Eutectic freeze crystallization is a technique to separate aqueous solutions into ice and solidified solutes simultaneously by operating at the eutectic point 1, 2. In principle, both organic and inorganic aqueous solutions can be separated, but this work is aimed at the separation of the latter. A typical phase diagram of a water-salt binary system is depicted in figure. First point D is the eutectic point. Cooling of a solution with a temperature and composition of point A causes the temperature to decrease until point B is reached. At point B, ice is formed, which increases the concentration of the liquid phase. The system follows the line B to C, which enlarges the amount of ice and further concentrates the liquid phase. At point D, the ice line intersects the solubility line of the salt and its saturation concentration is reached. Further cooling will result in the simultaneous formation of ice and salt. These two solid phases are completely separated. No solid solutions and no inclusions are formed when the growth process is carefully controlled. 3. Furthermore, the density difference of ice and salt is typically in the order of 1,000 kilograms per cubic meter, which makes the separation of these solids by force of gravity feasible. EFC is a separation technique that can be applied to most aqueous solutions of well-soluble salts. Compared to evaporative crystallization, which is the conventional technique to separate well-soluble salts that have a solubility with a low temperature dependence, from their solution, EFC requires less energy. 4. Cooling crystallization, which is also a comparable conventional technique, is limited by the remaining solubility at low temperature, whereas EFC would in principle be able to achieve a 100% separation of the solution into ice and salt if no purge streams are needed. The aim of this work is to experimentally validate the simultaneous formation of ice and salt crystals as two distinct separate solid phases in an indirectly cooled continuous suspension crystallizer. The model systems are copper sulfate pentahydrate ice and ammonium dihydrogen phosphate ice. Experiments were performed in a 250 milliliter jacketed glass vessel. The crystallizer was cooled indirectly with ethylene glycol. A Lauda RK8KP thermostatic unit was used to cool the ethylene glycol and pump it through the jacket of the crystallizer. The temperature inside the crystallizer was measured with a PT100 sensor connected to the RK8KP. Agitation in the crystallizer was provided by a magnetic stirrer. With continuous experiments, the feed was pumped into the crystallizer using copper sulfate and ammonium dihydrogen phosphate batch experiments. Starting with a clear supercooled liquid and adding ice seeds results in the formation of ice crystals without formation of salt crystals. This is observed in both the copper sulfate and ammonium phosphate experiments. Also, in both systems, starting with a clear supercooled liquid and adding salt seeds results in formation of salt crystals without formation of ice crystals. The presence of either of the two phases, or both at the same time, is easily determined by turning off the stirrer, salt settles, and ice conclusions. The eutectic temperature of ammonium dihydrogen phosphate water is 269.0 Kelvin. For copper sulfate water, the eutectic temperature is 271.6 Kelvin, corresponding with the value found in literature. Ice and salt, copper sulfate pentahydrate, or ammonium dihydrogen phosphate, can be crystallized as two separate phases by continuous eutectic freeze crystallization. These two phases are readily separated by force of gravity,